the introduction to probability. Okay, so don't worry, I'm not going to bore you. We will quickly go through probability, what is probability, and as and when where the concepts are little tough, nothing is tough here. So I will make sure that the pace is slow. Okay. So now what is probability? We all know that probability is actually the number of outcomes divided by the possible number of experiments, right? Or possible number of outcomes of an experiment. Now there are two definitions of probability. One is the classic model, right? And the other one is the relative frequency of occurrence. We'll go through both of them in the subsequent slides. But for now, classic model is when we say we roll a dice, right? Whenever we roll a dice, right? So if you say that I want a head, right? When I flip a coin, when I flip a coin, if I want a head, right? You know that there is only one head and there is one tail, right? So what you can do is you can say the total number of outcomes in which the event occurs. So if you flip a coin, you know that there is only one head, right, which is going to come, and the total number of possible outcome is 2. It can either be head or a tail. So it is 1 by 2. Okay. So a classic model of probability says the number of outcomes by the total number of possible outcomes. Okay. Next is the relative frequency of occurrence. It's actually the same. Okay. We'll see this whenever we have measurements. Whenever we say that we are going to draw 2 balls out of a bag, right? So it means the number of times an event occur, right? It will occur for 2 times. And the total number of opportunities for an event to occur, right? And the total number of balls in that sack is, or that bag is, say 10. So we can say 2 by 10. We'll come to the relative frequency part later. It is actually a little different from the classic model. Now let's understand this with a Venn diagram. Whenever we say we have an event A, right? It means that, so for example, if you are rolling a die and if you say that probability of getting 1 or 4 in the roll of a die, okay, so this is actually an event. So if I say, for example, 1 or 6, right? If you are getting only 1 and 6, so you are only interested in getting 1 and 6. So 1 and 6 is actually your event. So I can name it A. A is one event where you are ideally looking to get 1 or 6, right? So for example, you are playing a game, or you are playing Ludo, right? You either want 1 to win, right? Or you either want 6 so that your dice will come out of the home, right? So you are only interested in 1 and 6. So that's why I've said event A. So probability of getting 1 or 4 in the roll of a die. Or here we can say the probability of getting 1 or 6 in the roll of a die. So this is your event A. So likewise, you are playing with your opponent. Okay. The other opponent is also looking for something called, say, 2 and a 7, 2 and a 5, right? So for him or for her, the probability of getting 1 or 5 in the roll of a dice. So this is what she is interested or he is interested in. So this is event B and this is event A. Okay. So when you roll a die, you only have 1, 2, 3, 4, 5, and 6, right? So out of these 6 events, you are interested in 2 events, and then your opponent is interested in 2 events, right? So these are actually event. Now, as I said, the event A has a problem. You are actually looking to get 1 or 4. So you are only interested in your probability of getting 1 or 4, right? But the event C is looking for the complement, right? It is looking for 2, 3, 5, and 6, right? So you have event C, which is looking out for numbers like 2, 3, 5, or 6. You have event A, which is looking out for 1 or 4. So these are different events. Okay, so in a dice, we have only 6 outcomes, and that's why we had divided this into 2 parts, event A and event C. Now, what are mutually exclusive events? Okay, when the 2 events cannot occur at the same time, right? You cannot get, when you roll a die, okay, you won't get 1 and a 3, right? If you have only 1 die, you cannot get a 1 and a 3. You can either get a 1 or you can get a 3. So these are very mutually exclusive events. Okay, we'll get into the real example in the subsequent slides. Now, there might be occurrence that both are interested in getting a number. Say, for example, you are playing with, so you are A and the other person is C. Okay, you are interested in getting 1 and 4. The other person is interested in getting 1, 3, 1, 2, 3, 6, and 5. Right? So in here, both are interested in 1. So this is actually an event which both of you want. So this is actually the intersection, and we call it the intersection. Okay. Now, to understand what is a union and a intersection, so I'm going very fast because we all know about union and intersection. So when you have a union, you have A union C. A union C is actually telling you all the events inside A and C. So this is your A union C. Okay, so this is your A union C. The entire portion is, if someone is on, can you be on mute, please? Thank you. Okay, so this is the entire portion is, this entire portion is your union. It tells you the occurrence of A or C, right? Either A will occur or C will occur. So the entire probability will cover both event A and event C. But when I say that I am looking for intersection, what intersection means is, intersection is when the probability that event A and C occur, right? So you are looking for the numbers which are present in both the scenarios. So intersection is the probability that event A and C occur. So and is actually intersection, and or is actually union. Okay, so A intersection C here will be 1. Okay. Now moving on to the terms which we talked about. We have mutually exclusive events. When I say mutually exclusive events, is that two events that cannot occur at the same time, right? Two events which cannot occur at the same time, like heads and a tail, right? Both of them cannot occur at the same time when you flip one coin. Okay, one coin. So these are mutually exclusive events. Next is independent events. Independent event occurs. So it means that with the event A happening, there is no change in the probability of event B happening. Say, for example, if I eat something here at my home, it doesn't matter what you cook at your home, right? So we are very independent event. Okay, so they are not interrelated, right? Next is a dependent event, where one event is dependent on the other. Say, for example, if a stock, if the revenue of a company falls, right, the stock event or the stock market is going to crash for that particular company, right? Or we can say that revenue is dependent on the share price. Okay, so this is the occurrence of event A changes the probability of event B. Next is complementary events. Complementary events is when the probability that event A will not occur is denoted by PA dash. Say, for example, if I say head, the probability of getting head is 0.5. Okay, so not getting head is 1 minus 0.5. So this is 0.5. So this is a complementary event which is denoted by PA dash. Okay, we'll go through them again. Now, to explain you what is mutually exclusive event, say, for example, in a Walmart store, right, what is the sale of your sports equipment is very exclusive to, sales of grocery. So there is no relation to the sales of the sports section and the sales of the grocery section, right? So these are very mutually exclusive, okay, not dependent on each other. Next is the independent event. Say, for example, person A visiting a movie theater in India and person B visiting the Cineplex in Australia are two independent events. Okay, so they are not entirely, they are not at all dependent with each other. Next is the dependent event, where, say, for example, if there is a monsoon season, right? So automatically I know that the sale of umbrella is going to spike up, right? Because this is a necessity in the monsoon season. So the spike in sales of umbrellas in Walmart is dependent on rains and thunderstorm, right? Next, we'll see a complement of an event. A client agrees to invest in a mutual fund in the company, right? And the complement is the client does not agree to invest. Say, for example, another example will be whether my machine learning algorithm will approve a loan or not approve a loan. So event A is approving and event A dash is not approving. So there are two events which are very complement to each other. Okay. So before we move on to the rules of multiplication, if you have any questions, these are very basic terms which I wanted to show you before I move into the subsequent sections. Okay, if you have any question, drop me on chat. Okay, rule of multiplication. Now we all know that there are certain rules in probability which we'll closely look into. Say, for example, the probability that event A and B both occur, right? So you have two events, event A and event B. Okay. For that, the rule of multiplication say that you have probability of A and probability of B given that the event A has happened. Okay. Now, so can someone tell me what is the probability of that if you flip two coins, what is the probability of getting head in both of these flipping of coins? Okay. So now if I flip one coin, there is going to be head and this is going to be tail, right? So probability of head is 0.5 and the probability of tail is also 0.5. Okay. So what you are doing, you are flipping two coins. You are flipping two coins. So you have head, you can get either head, head, you can get tail, tail, you can get head and a tail, you can get tail and a head, right? There are only four outcomes. So what is the probability of getting head in both of these flipping of coins? Okay, let's see some answer.
Is 1/4.
It's going to be 1/4, right? You are going to get head in both these flipping of coins. So there is only one chance where you get two heads, right? So out of these four outcomes, only one event might happen that both will be head. So it is 1/4. Reiterating again, what is the probability that if you flip two coins, what will be the probability of getting heads in both of these flipping of coins, right? So if you flip two coins, right, you have two coins, coin 1 and coin 2, right? What are the events which might happen, right? First is you can get either a head or a head, head here, head here. You can get a tail and a tail, tail here, tail here. You can get either a head or a tail or a tail or a head. So you have only four outcomes, right? Possible outcomes. And out of that, I have asked you, what is the probability of getting heads in both of these flipping, right? Both of these flipping. So this is only one option. So 1/4 is the answer. Likewise, if you have any question, do let me know. Okay. Likewise, in two rolls of dice, what is the probability of getting 6 in both?
1/36.
1/36. Because if you have two dice, right? If you have two dice, what will happen is You can either get a 6 here or you can get a 6 here. And the total number of outcomes will be 36. Okay, just like we had 4 outcomes, in total we have 36 outcomes. So the answer is 1 by 36. Next is, there are 10 candles in a plate. Sorry, candies in the plate. 2 green, 2 yellow, 2 orange, and 1 red. If I pick 2 random ones, what is the probability of getting both yellow?
1 by 5.
It is going to be 1 by 5. Right? Any questions? So you have total 2 yellows, and the total number of outcome is 5 plus 2, 7, 7 plus 2, 9, 9 plus 1, 10. Right? So it is going to be 2 by 10, which is 1 by 5. Okay.
Alanka, I think it will be 1 by 10 C2, na? Because we are picking 2 at random, so total possibilities are 10 C2.
Right. Anyone also agree with? Is it Sachin or?
It will be 1 by 10 C2.
It will be 1 by 10 C2. Can someone answer whether 1 by 5 is right or wrong? See, I am not replacing them, right? So for example, if I'm picking 1 and that event is not, so for example, if I picked 1, which is yellow, so the next time you pick something else will be 1 by 9, right? But here I am picking 2 at once. So the answer here, I think, will be 1 by 5. We'll go to the one which you are talking about, right? So the question might be tricky, but the answer is going to be 1 by 5 because we are picking 2 at once, okay? Not 1 by 1, okay? Next up, we'll look into the rule of addition. Just like we have the rule of multiplication, we can also solve this using the rule of multiplication, which I will do after a certain point of time. But for now, since the sample space is very small, say for example, 2 number of coins, or you have say 2 dice, right, or 10 candies. So that's why I've used a manual approach, but we can use the rule of multiplication as well. Now, rule of addition is something where you have PA union B, which says PA plus PB plus PA intersection B. So it means that the probability of event A or B, right, occurring is actually the probability of event A occurring, probability plus probability of B occurring, minus, it should be minus, I'm really sorry. So this will be minus, this is correct here, minus the probability that both event A and B occurs. Now, why we are deducting intersection of A and B? Because when I'm taking A into consideration, I'm already taking this part, right? Whenever I'm taking P of A, it's actually taking this part. And whenever I'm taking P of B, it's actually taking this part, the entire B. So this A intersection B is getting counted 2 times, right? So that's why I'm deducting P A intersection B once. Okay, so this is the rule of addition. Don't need to mug this up. Okay, we will go through them again in some of the examples. Okay, just wanted to show you that there is a rule of multiplication and rule of addition. Now, the next thing which is very easy for you now is factorial. Okay, factorial of a non-negative integer n is denoted by n factorial. So this sign is actually factorial, and is the product of all positive integers less than or equals to 1. So for example, whenever I say 2 factorial, it's actually 2 into 1. When I say 3 factorial, it is 3 into 2 into 1. When I say 4 factorial, it's 4 into 3 into 2 into 1, right? So this is actually factorial. And please remember, 0 factorial is 1, I'm not going to derive why 0 factorial is 1, but the factorial of 0 factorial is 1. Okay. Now coming to the formula of permutation and combination. Now to understand what is the difference between permutation and combination, we have to understand that permutation is when the order is important, right? And combination is where the order is or position is not important, right? Say for example, example of a lock. Say for example, you have a suitcase, right? In a suitcase, you might have a lock, right? So you have 1 or 2, okay, you have 1 or 2 or 3 or 4. And now you can change this, right? You can change this based on the roller. So the order is very much important because 1, 2, 3, 4 and 2, 1, 3, 4 are very different, right? So in that case, permutation is the one which you should apply. Now, if I ask you to select a group leader out of all 10 of us, right? So, and a group leader and say, for example, a captain, right? A group leader and a captain, or say a captain and a vice captain, right? So the order is not important. You can choose as and when you want, right? So this is a example of a combination, right? If I ask you to select 3 people out of 10 of us, right? Out of 10 of us, you can select any random 3 people. So either you select, say for example, me or person 1 or person 2. It doesn't matter whether you select person 2 first and person 1 first, and I am the one at the end, right? So the order is not important. So when the order is not important, it is combination, right? The order is not important, it is combination. When the order or position is important, we call it permutation. Okay. Next is permutation and combination with examples. Say for example, whenever you have a lock, as I give you an example of lock, so you can have 0 up until 9, right? 0 up until 9. So you have 10 combinations for each of these roles, right? So you have 10 combinations for the first one, 10 combination for the second one, third one, and fourth one. So you have total 10,000 combination. So the formula for permutation, right, is going to be n to the power r for this scenario. Okay, I will come to the other formulas as well. So when you have a lock, you want to find out the number of patterns in the or number of combinations, key combinations. You perform this with n to the power r, right? So you have 10, and the number of combinations you will have is 4. So you have 10 to the power 4, which is 10,000. Next is, so this is with repetition. So repetitions are allowed, right? The repetitions are allowed in a key combination. You can repeat the number, not a problem. 0, 0, 0, 0, right? 1, 1, 1, 1, right? You can repeat as many times you want, right? 3, 2, 1, 6, as many times you want. So this is going to be n to the power r. So permutation with repetition is n to the power r. Next is permutation without repetition. So for example, in how many ways we can select 3 players out of 5? The first selected becomes the captain, second the vice captain, and third the treasurer, right? So now the entire scenario has changed. So you have selected the first person as captain, the second one as vice captain, and third one as the treasurer, right? If you select person 1 as captain, 2 as vice captain, and 3 as treasurer, and if you change this to 3 to 1, the entire combination changes, right? So this is permutation without repetition. The order here is important and it is without repetition. So in that scenario, you will have a formula NPR, which is n factorial by n minus r factorial. Don't need to memorize this, but you should have a basic concept of permutation and combination. Okay, here n is the total number of selection. Okay, and r is the number of selection. Okay, so n is going to be 5, r is going to be 3. Just put it here. So you get 5 factorial by 5 minus 3 factorial, which is 2 factorial. So if I do this for you, so 5 factorial by 2 factorial, which is 5 into 4 into 3 into 2 into 1 by 2 into 1. So 2 gone, you have 60. Right? So there are 60 combinations in which you can select permutation in which you can select 3 players out of 5. Okay, provided that the first one becomes captain, second vice captain, and third is treasurer. Now we come to combination without repetition. Okay, I will come to repetition after this slide. So combination without repetition. In how many ways we can select 3 players out of 5? So you can see the difference, right? So whenever in permutation, I make sure that our position is important, right? So whenever the position is important, you have to make sure that you are using permutation. But here, see, the position is not important. So I am selecting 3 players out of 5. So I will just use a combination formula here. So it is going to be NCR, which is n factorial by n minus r factorial into r factorial. So for here, it will be 5 factorial by n minus r, which is 2 factorial, and r, which is 3 factorial. So it's going to be 5 into 4 into 3 into 2 into 1 by 2 into 1 into 3 into 2, right? So this gone, this 3 gone, this is 2, so you have total 10, 5 into 10, which is 10. So the basic difference you can understand here, permutation is without repetition and combination without repetition. Now the question has just changed a bit, and that's why the formula has also changed. In permutation, the order is important. So you have an order here. See, the order is there. So that's why you have used a permutation formula. But whenever your order is not important, so you can select any 3 people, random people out of 5, right? And this will give you an option of answer of 10. Right? Now we'll come to combination with repetition. Now this formula, you don't need to remember this, but just for a basic understanding that whenever you have a combination with repetition, for example, in a store, there are 5 varieties of juice boxes. You want to buy 3 bottles. How many possible combinations you can buy? Now this is a repetition scenario because you can buy 3 bottles. You can buy any 3 bottles of the 5 varieties. In that case, this formula will not work. Okay, use this formula, r plus n minus 1 factorial by r factorial into n minus 1 factorial. So if you put 5 and 3 here, you will get an answer of 35. Okay, no need to memorize, nothing to do with formulas here. Just wanted to show you. So for example, if someone asks you any question in interview or a puzzle question, you are better prepared to answer these questions. Okay, nobody is going to ask you to solve this equations. Now a sample probability question, if 2 dice are rolled, what is the probability of getting the sum of numbers greater than 7? So you have 2 dice. You have 2 dice. All of them can have numbers from 1 to 6 and 1 to 6. So what is the probability of getting a sum of numbers greater than 7? A sum of numbers greater than 7 can be, say for example, 3 here and 5 here. So this is greater than 7 because 3 plus 5 is 8. Right? 2 here and a 6 here. 2 here and a 6 here. So this is again 8. Right? You can have 5 here and a 5 here. So this is 10. So all of them are greater than 7. They are greater than 7. greater than 7. Now to solve this, what we'll do, we can create a chart like this. So you have two possible outcomes. So the sum of numbers of die can be either 2 or 3, because it cannot be 1, right? Because the least you can get in one dice is 1. So 1 plus 1 is 2. So the minimum number after the sum is going to be 2. And likewise, you will get up until 12, because the maximum you can get in a die is 6 and a 6. So I have asked you that what is the probability of getting the sum greater than 7? So greater than 7. So it cannot be anything here, right? You have to count from here to here. So the probability of getting 8, the sum 8, is either with 2 plus 6 or 3 plus 5 or 4 plus 4 or 5 plus 3 or 6 plus 2, right? So there are total 5 ways you can get a sum of 8. Likewise, there are 4 ways you can get 9. And 3 ways you can get a 10. 11 ways you can get, 2 ways you can get 11, and 1. So if you add all of them, how much you get? 9 plus 3, 12, plus 3, 15. So there are 15 ways in which you can get 8, the sum greater than 7. Sorry, the sum greater than 7. And how many total number of outcomes are there? There are in total 36 outcomes, right? So this is going to be 15 by 36, which is my answer. Likewise, if I ask you what is the probability of getting the sum of numbers greater than 6, so in that case, you will also consider greater than 6, right? So this will be entire portion which you will consider. This entire portion, right? So we'll add 1, 2, 3, 4, 5, 6. So here it was 15 plus 6, 21. So the answer was going to be 21 by 36. Now it is the so if you look into the rolling of a die, only one die, you can either have 1 or a 2 or a 3 or a 4 or a 5 or a 6, and each of them will have a probability of getting 1 by 6. So 1 by 6 is the probability. So that's why 1 by 6, when you do it in decimal, it is going to be 1.67, right? So each of them has a probability of 1 by 6. And if you add 1 by 6 times, so 1 by 6 plus the total probability is going to be 1, right? So one thing which we need to understand is the total probability, the sum of all the probabilities of an event is going to be 1. Now, if I flip 2 coins, if I have 2 coins, coin 1 and coin 2, right? I can get a head and a tail and a head, so head and a head, tail head and tail, right? So you can see the probability of getting one head, right? One head is 1. Number of head is 0.5. I'm sorry, it is 0.5. Getting no head is 0.25, and getting 2 heads is also 0.25. Now, how did I calculate this? So probability of getting no head, zero head is only possible when you have both of them as tails. So if you have 4 events, out of them only one event is both tails. So it is going to be 1 by 4, which is 0.25. So that's why we have 0.25. Number of heads is equals to 1. So how many cases you have one head? You have 2 cases, one here and one here, where you have only one head. So it is going to be 2 by 4, which is 1. 2 by 4, which is going to be 0.5. 0.5. And likewise, of getting 2 heads, the probability of getting 2 heads is only 1. It is only 1. So it is 1 by 4, which is 0.25. 0.25 here, 0.5 here, and 0.25 here. So when you are flipping 2 coins, the probability of getting 0 head or no head is going to be 0.25. Probability of getting 1 head is going to be 0.5, and probability of getting 2 heads is going to be 0.25. Okay. Now, if you flip the coin 10 times, so I have flipped only 2 times, right? I am flipping only 2 times, and this is my graph. This is my graph. This is my graph. 0.25 to 0.5 to 0.25. Likewise, if you flip 10 coins, okay, we'll see this and we'll do this in Python also, that if I flip 10 coins, the probability of getting 5 heads is going to be the most, and it is going to be 0.25. And as and when the least number of heads and the most number of heads is very low, so we are following a normal distribution, right? So this is the probability of getting number of heads. So what we learned here is we learned the sum of all the area would be 1. So if you sum them out, okay, so if you sum them out, it is going to be 1. Likewise, if I show this small example, 0.25 plus 0.5 plus 0.25 is going to be 1. So the entire area is going to be 1 in all the scenarios. Okay, we'll look into the next section, which is the binomial distribution. But before that, if you have any question, do let me know. I know I have gone very fast because we will spend the most amount of time in coding, and all of these concepts will be crystal clear when you go through the Python examples. Okay, we'll do a lot of examples as well. Okay, we'll see how we can find probability if there is a defective bulb in a production line and all of them. Don't worry about this. Before that, if you have any question, do let me know.
So we talked about mutually exclusive events. So mutually exclusive events can be independent and dependent both, right?
It can be dependent and independent both, yes.
Okay.
Right. So whenever you have a mutually exclusive event, the basic idea behind is the one does not affect the other, right? So one event is very exclusive to the other event. But ideally, if you see that if there is a dependent event, then in that case, there might be some exclusivity. And there is one catch to this. We will come to this when when I am going to explain this using Python, because it will be easy for me to explain through numbers. Okay. Any other questions? Okay. So I will quickly go to Menti. So let's look into very basic probability questions. Okay. Please use the link. One more left. Don't worry if you're not able to answer. It's actually very easy, but even if you are not able to answer, don't worry about it. We will understand everything when we go through the Python exercise. Okay, one more guy left. I'm not sure who it is. Let's start. One second. Great. So the probability of rolling a die and getting the number 4 is 1 by 6 because there is only one event 4 and the total number of event so only one outcome 4 and the total outcome is 6. Right. So 1 by 6. Moving on to the next one. Sorry. There's some issue with the Menti. Don't worry. Just give me a second. If you roll 2 fair dices, the probability of getting a sum of 2 numbers as 8 is more than the probability of getting the sum as 2. Is it true or false? The probability of getting sum is equals to 8 is more than the probability of sum as 2. Right? The probability of getting the sum 8 is obviously greater than the probability of getting 2 because we will have more outcomes which will sum up to 8. Right? A ball is drawn at random from a box containing 20 red, 30 yellow, 10 green, and 40 blue balls. Find the probability that it is either green or blue. It is either green or blue. it is going to be 0.5. Why 0.5? Because the number of green balls are 10, the number of blue balls are 40, so total 50, right? And the total number of balls are 20 plus 30 plus 10 plus 40, which is 100. So you have 50 by 100, which is 0.5. Okay, those who got 0.2, I think there was some silly mistake, or if you have any doubt, do let me know. In how many ways can a committee of 4 people be chosen out of 10 people? A committee of 4 people be chosen out of 10 people. Order is not important. Answer is going to be 210. Why? Because it is 4 people out of 10 people. The order is not important. So we'll do 10C4. If you do 10C4, calculate how much you get. Okay. Last question, very easy. Two coins are tossed together. What is the probability of getting one head and one tail in this experiment? One tail and one head. What is the probability of getting one head and one tail? One head and one tail. Great. So all of us have answered 1 by 2 because we have total 4 outcome: head, head, tail, tail, head, tail, tail, head. And we are looking for one head and one tail, which is head, tail, and tail, head. So 2 by 4, which is 1 by 2 or 0.5. Okay. Please follow along me if you have your Jupyter notebook open. We'll start with creating some random numbers. I hope you all know how to create random numbers, but still I will go through 1 or 2 examples to create random numbers. Right. We'll start with NumPy. Everyone ready, or you need some time? Do let me know over chat. I will probably take 2 minutes of break. Can I start, guys? Great. Okay, so we'll start with import NumPy as NP. And as we know, we can use np dot random, right? Dot rand, and this will give us a random number between 0 to 1, right? Each time you use np dot random dot rand, this function will get you a random number between 0 and 1. Now, previously also, you guys also asked me that every time I run it, I will get probably a number, and how can I reuse or regenerate the same number? So earlier I told you this is random state, but my apologies, random state is used in scikit-learn, which will go through in machine learning, but here we'll use seed, right? So you can use np dot random dot seed. So for example, I use the seed of 50, right? I use the seed of 50. And now if I type in the same thing, right? If I type in the same thing, what I will get is the same number again and again. Okay. See, I'm getting the same number again and again. You can change the seed to any number you want. Okay. So if someone is using the same seed which I am using, he or she will get the same random number. Okay. If I change this to 50 and someone else is using a random seed of 50, he or she will get the same number which I am getting here in this screen. Okay. So let me use 555 and all of us can use 555 for better reference. Okay. I hope you all are getting 0.7178. Okay. Now, what if I want to generate not one number, right? I want to generate more. Say, for example, I want to generate 5 random numbers. I'll quickly hit on rand 5. It will generate 5 numbers for me between 0 and 1. It will generate 5 random numbers in an array. Okay. It will generate 5 numbers in array. Now, if I want to flip a coin, right? If I want to flip a coin, I know that there are only 2 instances. One is a head and one is a tail. So how can I use this same function to generate for a head or tail? Now I know that the probability of getting head or a tail is 0.5. So I can say, okay, if it is greater than say 0.5, right, it will generate me 2 instances. One is true and a false. So whenever I use a greater than 0.5, it's actually comparing the Boolean values. Okay, it is comparing all of these values. So it is comparing with the first one. If it is greater than 0.5, no, it is not greater than 0.5. So it is false. If it is greater than 0.5, yes, it is greater than 0.5. So it is true. Likewise, this is true, and this is false. So the ideal answer which you will get is true, false, true, false, and false. Okay, use the seed also. Use the seed in order to get the same value as before. Okay. Now, so I hope you got the Boolean value true, false, false. Okay. So the random number as and when getting generated, you are getting a value, right? So each time I run something, I am getting different values. Okay, because it is calculating with respect to whatever random number is getting generated, right? Okay, so if you run 3 of these commands, what it is creating, it is first creating a seed and then a rand with 5 random numbers between 0 and 1, and then it is comparing whether all these numbers which are getting generated are greater than 0.5 or not. So obviously the first point which was getting generated, or first number which was getting generated, was less than 0.5, so it's 5 false, greater than 0.5 true, and then false and true and false. Okay, hope you got the gist of it. Now if I want to find out the count, right, if I want to find out the count, so what I am saying is, if your 0.5, if the value is greater than 0.5, it is a head. Okay, so if value greater than 0.5, it is a head. Okay. So here, how many heads you are getting? You are getting 2 heads, true and a true, because you are comparing 0.5. Anything greater than 0.5 is actually a head. Okay, so you are getting 2 heads here and 3 tail. And if I want to count the number of heads, so what can I do? What can I do is I will quickly go through and let's do some. Right? And you're getting 2 because you have 2 true values here. You have 2 true values. So in total, you have 2 heads. You have 2 heads. Clear? Any questions, guys? I'm trying to go very slow. If you're confused, do let me know. Please follow along. If you have any question, do let me know. All clear, guys? Okay. So this was very simple. Okay. Now, if I want to generate not one-dimensional array, but rather I want to give rows and columns. So what can I do is I'll just type in np.random.rand. Okay, and a 2 and 5. So it will give you 2 rows and 5 columns, right? You get 2 rows, 1, 2, and 1, 2, 3, 4, 5. 5 columns. You got 2 rows and 5 columns. Right? Now this decimal is something which we don't want to do 0.5 every time, right? So what we can do is we can do one thing is, say for example, flipping a coin. Okay, greater than 0.5, it's actually a headache. So what we can do, we can generate numbers, right? So I will use a function called randint. Okay, it will start from 0 and it will end before 2. So it will ideally give you 0 and a 1. And in total, it will generate 10 numbers for you. Okay, so the lower limit is 0. The higher limit is 2 minus 1, which is 1. So it will generate only zeros and ones and will generate total 10 numbers for you. Okay, see, it has generated 10 numbers for you, 0 and 1. Right now, from this, if you see, if you want to create the sum again, you can do on your own. Sum in brackets np.random.randint 0, 2, 10. Okay, which is 5. So in total, how many heads you are getting? You are getting 5 heads. Any questions, guys? Now, if someone can tell me, if I want to roll a die, if I want to roll a dice, okay, how to tweak this? What should I do? If I want to generate the numbers in a
7
die,
instead of 2.
yes, we will do 7 instead of 2. And then one more thing,
1, 1, 7.
1, 7, right? We'll do 1, 7, and 10. So it will give you, and how many outcomes are there in a dice? 6, if I'm correct, right? So if we want to do it for a 1 die, we'll ideally get 1, 2, 3, and 6. So it generated 6 numbers for you. But ideally, if you want to generate, say, 100 numbers, right, you can run all of them and you will get numbers between 0, 1, and 6. Okay, and total 100 outcome. Okay, so you actually, what you did, you roll dice 100 times, right? So you are getting the simulations. Now let's plot something, okay, for rolling of a dice. Okay. Now, if I want to plot something, the first thing which I need to do is import matplot, right? Matplotlib dot pyplot as plt. And then we have to import Seaborn, right? These are the two libraries which we require. Import Seaborn as SNS. Okay. Now, if we want to, create a seed first so that all of us get the same result, let's do one thing: np.random.seed. And as I said, we'll be using 555 in the entire class so that all of us are on the same page. Now let's create something. Let's create for the same value, right? Let's create for the same value. So a will be is equals to np.random.randint 1,7 and do it for, say, more number of simulations. So let's do for 6,000. Okay. And now what we need to do is we want to show this, right? And I want to show the number of counts. So I will use the count plot. Okay. And in X, I will pass the numbers and then plt dot show. Right. It took some time to generate the result because we are running this for 6,000 simulations, right? So if I run it again and again, the plot won't change because we are using the same seed. Okay. Please follow along. Any question, do let me know. So this is just from here, which was a simple way of generating number in an array, right? What we did is we generated it on top of a visualized layer using matplotlib and Seaborn. Okay, we used Seaborn for count plot and we used matplotlib to show the visualized version. Got it? Now, so this was a simple way we can show the result through, for example, for a dice or for heads or a tail, right? A coin or anything we want. Let's do one sample question. Any question? Okay, let's do this one. So for example, this is the question. Okay, so this is the question for you. If 2 dice are rolled, what is the probability of getting the sum greater than 7. We all have solved this. The answer was 5 by 36, right? The answer was, sorry, 15 by 36, if I'm not wrong, right? 15 by 36. It's 0.416. Could have done this here only. 0.416. Okay. Can someone tell me how should we start? You have 2 dice. So first we have to initialize with first we have to initialize with 2 values, right? We have to initialize with 2 dice. Sorry, we will initialize with 2 dice. So let me take this one and paste it here. So the first one is, say for example, we are using die 1 here. Okay, die 1 is np.random.randint 1,7, and let's do for only 10 simulations. Okay, only 10 number of times. Likewise, we'll do for die 2, right? We'll do for die 2, which will again generate 1, 2, 6, right? 10 times, right? And then what we can do something like die sum equals to okay. If you want to see, so there must be something on die 1 and die 2, right? And when I sum both of them, you can see 8, 8, 8, 7, 8, 7, 9, 8, 5, 5. And I want to check how many of them are greater than 7, right? So what can I do? I can do sum and then in bracket just to check die underscore sum is greater than 7. So there are 5 instances where the value is greater than 7. So 1, 2, 3, 4, and 5. So 5 instances where the value is greater than 7. Now we have to understand that we are repeating this task only for 10 times, right? We are repeating this task only for 10 times. So now what happens is you have 5 instances here and you have done this for 10 times. So 5 by 10 is going to give you 0.5, right? Which is closer to 0.416, but not, much closer. So we have to do this for a higher number of simulations. So let me do one thing. Let me change this to somewhere around, say, 1,000,000 record. Okay.
Alankar, do we here we are doing directly pairwise, like die 1 every instance of die 1 and die 2 one by one we are doing? Do we need to do that way, or like every pair of die 1 with every instance of die 2 like that?
No,
So
no, no,
it
no.
becomes 100.
No. It's like you are creating values. You are rolling the die one by one. Okay. So you have 2 dice. So once you roll the first die, you are getting 3. Okay. The next time, say you roll something, you get a 2. So 3 plus 2 is 5. So that's why I've given you values like 5 and then followed by. So it's like one instance at a time.
So you're saying we are rolling both the dice together here?
Together, yes. We are
Okay.
rolling both the dice together. Okay. Now it's the same thing. You have to do die sum, right? And then you have to check whether the sum is greater than 7. Let's see. See, the answer you are getting is 416742. And the number of instances you have is 10 million. If you divide this by 10 million, you'll get somewhere around 0.4167. You'll get 0.4167, which is very near to your 0.416, right? And each time you run this, you'll get a different set of answer because we are not using a seed here right now. But the answer is really going to be closer to 416, right? This is going to be 416. Any question, do let me know. So it means that the number of samples which you collect every time is actually the more number of samples you create, the better will be your accuracy. Okay. And if you do this for probably 100 million times or 200 million times, the answer will be more marginal. Okay, with very less marginal. So what you get here, I hope you all understood that how do we actually use probability in Python, right? I gave you a very simple example using a die, okay, and we'll do or we'll perform analysis on top of different type of questions. Like the questions might be production units, might be drawing number of balls, right, out of a bag, and so on. Fine. Any question, do let me know. If it is clear, we'll move on to the next section. If you want me to repeat any section here, okay. So with that, we have seen a small example of probability, how we can do this on top of Python. And now we'll move into probability distributions. Okay, so there is not much we will go through in today's section, but ideally we will understand what is a binomial distribution. Now, what is a binomial distribution? So we have seen instances where we have two types of outcomes, either a 0 or a 1, right? We have outcomes like whether the loan will get processed or will not get processed, right? Whether the customer is going to churn from my system or it's not going to churn from my system, right? So these are binomial distributions because you have two different possible outcomes. Okay, what we do in a binomial distribution is that we experiment it with n repeated trials. So just like we have seen, we have performed rolling of a die with a million repetition, right, in our Python example. And whenever you have a head or a tail, you have only two possible outcomes. The outcome can either be a success or can be a failure. So that's why we call it binomial. The probability of success is denoted by P and is the same on every trial. So whenever whenever you have a binomial distribution, just imagine a coin, nothing else. So a coin, you can repeat the number of trials as many times you want. So you have n repeated trials. You have only two possible outcomes, either a head or a tail. So the second coin is done. The third point is probability of success is same on every trial. So each time you flip a coin, you know that the probability of getting a heads is 0.5. It's not going to change. The probability of getting a tails is 0.5. It's not going to change. So the probability of success, which is P, is same on every trial. And the trials are independent. That is, the outcome on one trial does not affect the outcome on the other trials. So it's very easy to understand that if I am flipping a coin for the first time I am getting a head, this head does not affect the second time I'm going to flip my coin, right? So this trial is purely independent. So three things which we need to understand is it has binomial distribution has only two outcomes. For every trial, the probability of success is going to be same. For every outcome, it is not affecting the other outcome. Okay, so just imagine a coin in a binomial distribution. Now, a binomial distribution has a formula. You don't have to mug up this formula. Don't worry about it if you don't understand. But I'm just going through the basic of it. We'll see how to do this in Python, and Python can do this on its own. Okay, so we just need to understand the Python function, not the binomial distribution formula here. But to go to the basics here, the number of success that results from the binomial experiment is x. So when I say P of x, the x is the number of success. N is the number of trials. You see N here, which is the number of trials, how many trials you want to perform, whether you want to do it, flip the coin for 10 times or 20 times or 30 times. It is N. The probability of success on individual trial. The probability of success, for example, if you are performing this on top of a coin, right? Your probability of success is 0.5. Probability of getting a head is 0.5. So P is basically 0.5. Binomial probability. The probability that an n trial binomial experiment results in exactly x successes when the probability of success on an individual trial is P. We know that the individual trial success is 0.5, and I want to find out how many times I am going to get a head. Okay, so exactly x successes. Let's understand this with an example. So this theory is very difficult to understand and it's very boring also. Let's do this with an example of coin. So if you flip a coin 4 times, what is the probability of getting one head? Okay, so if you have this formula, right? If I want to do this with the formula, let's see how I can do that. So the formula was P of x is equals to n factorial by x factorial and then n minus x factorial p to the power x 1 minus p n minus x. I hope this was the formula, right? Yeah. Now you don't need to remember this. Okay. Now I want to get probability of one head, exactly one head, right? So here we have how many coins we have? We have 4 coins. So n is going to be 4. Sorry, we are flipping the coin 4 times. So the n is going to be 4. The number of times you are performing, right? The number of trials in the binomial experiment. If you see n here, the number of trials, right? So we are going to perform 4 trials. So n is going to be 4. So let's put 4 here. I am going to get one head. I am going to find the probability of one head, right? So it is going to be x is going to be 1 factorial. If you don't understand, x is actually the number of successes that result from the binomial experiment. So I am looking for only one head, right? And then 4 minus 1 factorial. And probability of success, what is the probability of getting a head is 0.5. So this is going to be 0.5. So this p is going to be 0.5 and x is 1. We all know 1 minus 0.5, 4 minus 1, right? So this is 4 into 3 into 2 into 1 by 1 into 3 into 2 into 1. right? 4 minus 1 is 3. So 3 factorial is 3 into 2 into 1 into 0.5 into 0.5 whole to the power 3. So we have 4 into 0.5 into 0.5, 0.5 into 0.5, right? So if I do a 4 into 0.5 is 2, 2 into 0.5 is 1, 1 into 0.5 is 0.5, 0.25. So answer is going to be 0.25. And if you remember, as I told you, you don't need to understand this formula or mug up this formula. Okay. What you will do is you will use Python to find out the answers. So I hope this is clear. If you flip a coin 4 times, what is the probability of getting one head? The probability of getting one head is 0.5, 0.25. Okay. Now, one thing which you need to understand is the mean of a binomial distribution is n into p. Okay. So here, if you see, if you flip a coin 4 times and the probability of getting a head is 0.5, so this is your probability P, and this is the number of times you want to perform, right? So n into P, which is 4 into 0.5, is going to be 2. It is going to be 2. This is one thing which you need to remember, right? Because at times in MCQ, if you sit on an exam or a test for companies like Mu Sigma, yeah, entity data, who perform a lot of statistical analysis, even if you join any organization for example, data scientist in a risk domain, right? Or insurance domain. So you have to work with a lot of actuaries. You have to work with a lot of actuaries, right? And in there you will find a lot of scenarios where probability is used and binomial distribution is used. So in MCQ questions, they ask you a question like, what is the mean of a binomial distribution? So it's going to be n into p, the number of times you perform the analysis and the probability of each event. Okay, just remember it with an example. Right? If you flip a coin, then on average you will get 2 heads. Okay, on an average you will get 2 heads. We'll see this through an example also. Now, if once you have the mean, you can also have the variance. Now, variance is going to be n is going to be 4, p is going to be 0.5, and q is the complement. Complement is 1 minus p. Q is 1 minus p. So 1 minus p is actually 1 minus 0.5, which is 0.5. So 4 into 0.5 into 0.5. This is going to be your variance. This is going to be your variance. So your variance here is how much? 1. 4 into 0.5, 2. 2 into 0.5, 1. And your standard deviation is root under of variance. So again, it is here 1. Root under of 1, which is 1. Okay, a little theoretical, but we are able to understand. So n is the fixed trials. So here you have 4 trials. That's why fixed trials. N. P is the probability of success, and Q is the probability of failure. So if you don't get ahead, you actually are getting a failure, which is 0.5. So head is a success and tail is a failure. Okay. Hope you all have understood this. Any questions? Okay. Now the second one. We'll do this in Python also, but here we will find the solution. A manufacturer has 12% defect rate in production. The buyer decides to test 20 random pieces and will accept the supplier if there are 2 or less defectives. What is the probability of getting accepted? Before we start, can someone tell me what is the P here, what is the N here, and what is the X here?
P defect rate is 0.12, N is 20.
0.12. N is 20.
20. And X is like if 0, 1, and 2.
0, 1, and 2. Right? Those who have not understood, we are trying to get, we are trying to test that if it is, the defect rate is whether it is 12%. Okay. And there is a buyer who decides to take 20 random samples. So N is going to be 20 because I'm taking 20 random samples, right? And accept the supplier if there are 2 or less defective. So it might happen that none of them are defective. It might happen that 1 is defective or 2 is defective. If it is going to be 3, we are not going to take it. If it is going to be 3, we are not going to take it. Okay. So first we have to understand right. So N is equals to 20, X is equals to 0, 1, 2, and P is going to be say 0.12, right? Because this is the defect rate we are claiming. Okay. Now, first point is we have to find for individual X, right? If you remember, you have to find for individual X. So we'll find P of 0, P of 1, and P of 2, right? Now we have the formula P of X is equals to N factorial by X factorial, N minus X factorial, and it was P to the power X, and then 1 minus P to the power N minus X. Okay, I'm quickly going through it. Just X is 0 factorial, and then 20 minus 0 factorial. P is 0.12, X is 0, right? And then 1 minus 0.12, 20 point minus 0, right? And likewise you will do for, so this is for P of 0, you will do for P of 1 and P of 2, right? And once you get all of them, what you'll do is you will sum them up. Okay, you sum them up and you will get something, some answer. Okay, say for example we get a 0.4. Okay, once you do a P, once you get all the P values, P0, P1, and P2, what you'll do is P of 0 plus P of 1 plus P of 2, and it will give you some value. Okay, say 0.4, for example. I don't know. Okay, example. Okay, we'll calculate this using Python. No need to do this here, right? And with that, we will move on to the Python example where we'll perform similar set of analysis, how we can perform binomial distribution using NumPy. Okay. Okay, before we start with Python, I will quickly go to Menti again. Try to answer the questions of binomial distribution. Only 2 questions, no quiz. Okay, take your time to answer. Please use the chat box to get the link. Which of these is not the correct statement for binomial distribution? Come on, two more guys. Which of these is not the correct statement for binomial distribution, right? Okay. Okay. So we have learned that binomial distribution is independent of trial, right? So the second option is gone, because if I flip a coin now, it is not going to affect what was going to be the answer of the or result of the next flip, right? The second is the outcome of one trial does not affect the outcome of the other trials, right? This is correct. The outcome of one trial does not affect the outcome of the other trial. The first one is probability of success is same on every trial. This is again correct, right? So this will not be the answer. Every time you flip a coin, you are going to get 0.5 probability of heads every time, 0.5 of tails every time. So your probability of success is same on every trial. Every trial, your probability of success is going to be the same, right? So the option is 4. Each trial can result in 2 or more possible outcomes. No, each trial will have only one option. Either your loan is going to be processed or it's not going to be processed. Either you're going to get a head or you're going to get a tail, right? Moving on to the next one. A binomial experiment has 30 trials with a probability of success 0.25 on each trial. What is the mean of the distribution? We have just seen the formula of the mean of a distribution in a binomial scenario is n into q. N is the number of trials and n into p. N is the number of trials and p is the success. So 30 into 0.5, which is 7.5. Okay. 2.371, I guess you've made a mistake. It should be 30 into 0.25, which is 30 into 1/4. That is 7.5. I hope you all understand. If it is going to be a standard deviation or a variance, what you'll do n into p into q. So if I ask you for a variance, what we'll do is 30 into 0.25 into q. Q is 1 minus 0.25. That is 30 into 0.25 into 0.75. Right? So you just multiply 0.75 with the mean, you will get the variance. And if you want a standard deviation, you can just perform a square root. Right? I hope we all understood what is binomial distribution. Before I start, if you have any question to let me know. We'll start with binomial distribution now. Okay, so let us start. I hope all have joined. Okay, let us start with binomial distribution. Please follow along. So what we need to do is, since we have already imported NumPy, we will look into a function called np.random.binomial. Okay. Now, if I want to do this for a coin, right? We know that, and I want to flip one coin, and the probability of flipping is 0.15, right? And if I just hit on run, what I get is unbiased coin, either giving me, so I'm just flipping a single unbiased coin, and it is giving me a number, right? So this is a random number which is generating. You can do this for flipping two coins, right? And you again get a 1, which is again giving you an outcome, either 0 or 1 for the binomial distribution. And if I want to flip two coins, say for example, I want to flip two coins. And instead of doing this for a very less number, and I want to do this for say 1,000 times.
So can you tell again how random.binomial is working?
Okay, so if I just paste this number variable, what you get is it is giving you numbers from 0, 1, 2, right? So since I have given 2, so it is getting number from 0, 1, and 2, right? So
Yes,
if I
sir.
do this for 1, right, what you get is zeros and ones, right? So zeros and ones, and you are flipping this for 1,000 times, so you are getting output as zeros and ones, right? And probability of each of them is 0.5. Okay, for this, for an unbiased coin.
Okay, sir, got it.
Right? If you want to see this into visualization, let me just copy this code and I will reuse it. You guys can also copy it. Okay. Just comment this out. Now I have imported matplotlib and Seaborn, right, by default. And then since we have 2 points here, can we use this here? 2 points. Right. Right. So the probability of getting 0 heads and 1 head, right? Let me do one thing. Let me run this. Okay. If you remember, this exactly resembles what we have done here. Here. Okay, we are flipping 2 coins. Okay, and the probability of getting 0 heads, okay, is 0.25. The probability of getting 1 head is 0.5, and probability of getting 2 head is 0.25. The same thing we are doing here. Okay, out of these many random numbers, since I'm not using a here, just quickly delete it. What we are using is these 2 points. Copy this here so that you can better understand. So I have taken 100 trials. I have done 100 trials, and I want to check how many times head occurs 0 number of times, how many times head occurs 1 time, and how many times head occurs 2 times, right, in each flip. I'm simulating the result, and out of that result, it gives me a binomial distribution. It gives me a binomial distribution. It's the same which we have done here. Okay. Now, since we are doing this for only 1 coin, can we do this for 10 coins? Yes, obviously we can do this for 10 coins. So in that case, what will happen is, in the first instance, you have head and a tail and a head and a tail and follow, so on and so forth. And if I go back to here, can we do this for 10 coins? Yes, we can do this for 10 coins. We'll just quickly copy this and paste it here. Instead of 2 coins, what we are going to do? We are going to do for 10 coins. Everything will remain same, right? I will just rename this to 10 coins. This to 10 coins, right? And if I hit on enter, what will happen is, instead of 0, 1, and 2, it will give me a different set of probability distribution, right? Again, this is the binomial distribution, because the number of chances you get 0 heads is very less. The chances of getting all tails is very less. The chances of getting all heads in all these 10 coins is very less. But the chances of getting 5, right, 5 heads is very high. So that's how you see this is the binomial distribution. Okay, we have created a binomial distribution and it basically follows a normal curve. Okay.
So in this case, we are using seed, so maybe we are getting same output as you are getting. But even if we are not using seed, it should be the shape
Yes.
should be normal as well, right?
Yes, that's right. That's right. So seed is very much useful whenever you have a quantitative number. Okay, the one which we used earlier, where we used to get quantitative numbers. In that case, seed is very useful. But whenever we are performing this on a large simulation and we are looking into a graph, that doesn't make sense. But if you use a seed here, right? If you use a seed here, the number which you get in 2 coins, that will be exactly same for you and me if you use the same seed. Okay, but as and when you perform this simulation on top of lot of trials, what happens is that eventually the number of occurrence of each of these instances, like a head and a tail, will eventually be very close. So the difference is not visible here, but you will see the difference when you flip the coin and then try to print them using a seed. So both you and me, if you use different seed numbers also, will get different numbers. But eventually, since the number of trials is so huge, that will give you same set of results. Okay, that's why randomness is something which is very important in probability. It gives you ultimately the same type of output. If I do an analysis and you do an analysis on the same method, but might be our data is a little bit different, we will eventually get results which are very close. For example, whenever we have exit polls, right? You might be from different news channel. I am from a different news channel, but I predict that the ruling government is going to get, say, 200 seats. You are going to get a result which says 205 seats. So we are very close, but eventually there is a difference because we have not used the same random data, right? And if it is use the same random data, probably you will also see a result of 200 seats and I will also see 200 seats. Got my point?
Okay.
Okay. So that's why there is a concept called poll of polls, where you have 10 news channels doing the same type of analysis and they do some average on top of it. And they show the result that, okay, based on these 10 polls, we think that this government is going to get, or this party is going to get this number of seats. Okay, so if you want to make it a little beautiful, I think we can use something called a theme, but it's not mandatory. I just want to make sure that we all know this. I will just quickly write one code. It was sns dot set theme, and we can use a style. if I use something, maybe a white grid. Underscore. Yeah, you see, this is just for beautification, nothing else. The grades are visible now. Okay, I've just set up some style here, which is set theme, and I have given a white grid here, just to make sure that it looks a little better than the previous one. Okay, here it doesn't have any theme. Oh, it has a theme. If you want, you can add, not a problem. Okay, so now I will just want to introduce you to the SkyPy library, which is basically used. This module basically contains a large number of probability distributions as well as a growing number of libraries of statistical functions. We just wanted to show you a few examples, because from the next class onwards we'll be using SkyPy. So we can just import SkyPy. Say, for example, if I want to import binomial, we will heavily use SkyPy.stats here. Okay. And we'll see something called a cumulative distribution function, CDF. It starts from 2 and 20, something value of 1. Okay, let's do this with an example. Can we take an example? Okay, let me check. Okay, let's do this. Okay, so you have a question. It says a manufacturer has 12% defect rate in production. The buyer decides to test 20 random pieces and will accept the supplier if there are 2 or less defectives. What is the probability of getting accepted? Okay. Now, we all know that there were some parameters which we understood. N was 20 because we are taking 20 random samples. And then probability of defect was 0.12, which is our success parameter. And X was going to be 0, 1, and 2. Right? So let's do one thing. Let's create a function reject, right? And we can use a binomial function. So I'm not going to SkyPy right now. Let's solve this solution first. So np dot random dot binomial, right? And then there are 20 number of trials, or yeah, 20 random pieces. And then we have 0.12, which is the probability, right? And let's do this for 10 iterations, just to show you the result. And each time we take out a value or take out bugs, we can see that 5 are defective, 1 is defective, 3 is defective, 6 is defective, and so on, right? So in these 10 trials, we can see that 5 of them were defective. Okay, in the first trial, out of this random 20 pieces, 5 were defective. In the second trial, out of the 20 pieces, only 1 was defective, and so on. Right? Now, only doing this for 10 simulation won't work for us because the sample size is very small. So the simulation is also very small. So let's do this for a bigger number of trials. Say we do this for 1,000 at least. Okay. And then let's plot this out to check. Okay. Right, we have done this for 1,000 number of simulations. Right, we are taking 20 random samples at a time, and the probability value is 0.12. Okay, let's see how the graph looks like. Right, the graph look like this. So 0 defect, 1 defect, 2 defect, 3 defect, 4, 5, 6, 7, 8. Okay. This is how we are getting. Now, if I want to use the SkyFi function to just calculate the binomial value, I can do this. Since our x was 0, 1, and 2, we all remember it is 0, 1, and 2. So if I pass a value of 2, it will eventually take from 0 to 2. Okay. And then we have 20, which is the number of random sample, and the probability, which is 0.12. So ultimately the answer is going to be 0.5631. It is 5631. So if I go back to this, P of 0 plus P of 1 plus P of 2, the answer which we get is 0.5631. So this is actually our probability of getting accepted. So P of x is equals to 0.5631. So this is how we calculate it, right? What we did, we just used only one function called a binomial function, and then where there is something called the cumulative distribution frequency. Why this is cumulative? Because we are adding one after the other. Cumulative value 1, 0 plus 1 plus 2. Cumulative value. So for example, if you have production of 500 units in day 1 and 510 units in day 2 and 520 in day 3, So this is the frequency, but your cumulative frequency will be 500, 1010, and 1530, because we are adding 500 to 510. So this will get added to this. You have 1010, and this will get added to this, and you have 1530. So likewise, we are doing this for binomial cumulative distribution function. Right? Any question? Do let me know if you're not able to understand. Right? So reiterating it again. Now the question we have was, the defect rate was 12% in production. The buyer decides to test 20 random pieces and will accept the supplier if there are 2 or less defective. What is the probability of getting accepted? Okay. Now you say, for example, if you are the supplier, okay, you go to the factory and randomly take out 20 bulbs. Okay. If you take out 20 bulbs from the factory or from the manufacturer, and you check how many or count how many of them are defective, and if you see 5 of them are defective, you're not going to take it, right? You're not going to take it because you will not accept anything if it has more than 2 defects. It has more than 2 defects, you will not accept it. Okay. So what you did is you simulated these results. Okay. You could have done this for only once, right? You could have done this for only once. For example, instead of 1000, if I do only once, right? If I hit and run, there is only one chance that, see, I got 3 as the result. The number of defectives are 3. I'm not going to take it, so I'm rejecting it. Okay. The next time again, you run it, right? You got 0 defective. You said I'm going to take it, right? And so on. This is 1 because there is only one frequency. 5, you will say that no, I'm not going to take it. So you did it for 1000 times instead of once. You did it for 1000 times, and this is how you see that you got 0 defective bulbs for this many numbers, probably 60 or 70. You got 1 defective for say 200 and some numbers. You got 2 defective for 270 odd numbers, right? And then it's again decreasing. So based on this, you created a cumulative distribution function, okay, for the binomial theorem, for the binomial distribution. And based on that, you can get into a probability that, okay, 56% chance is that I am going to accept this. Okay, 56% chance. Now, if you want to make it very less defective, so I want either 0 defective or 1 defective. So I made it 1. If I run this, you see the probability of getting rejected is only 28% now. So if you have 0 defective, so you can see that the probability is very less of being defective. Okay. So the answer is 0.5631. Now, can someone tell me what is going to be the okay, please calculate the mean, variance, and standard deviation. Mean, variance, and standard deviation. You have the probability here, 0.56 and then 31. Please calculate the mean, variance, and standard deviation. Please calculate the mean, variance, and standard deviation. Please use this Menti link to answer your question. The question I have asked is, what is the mean, what is the variance, and what is the standard deviation? We know that the mean is 0.5631. We know the formula of mean and variance here, right? You know what is the probability which you have got. You know what is n and what is npq. You can get the variance directly. Please answer what is the mean, variance, and standard deviation up to 2 decimal points. Please note, this is your cumulative probability distribution. Okay, don't use this p in mean. This is not your p. Your p is in this question. Please guys answer. What is the mean and variance? So mean, please answer what is mean here. The formula of mean is n into p. Identify what is n and what is p here. This is not your p. This is your cumulative probability. Come on guys. P here is 0.12, right? The probability of defect. And n is the number of values which you have, or number of random pieces. So please calculate your mean and variance fast. Use this Menti link to answer your question. Come on, this is easy. Please answer. Five of you have answered. P into R. I think there is a silly mistake. It should not be 24. The answer should be 0.12 into 20.
I think Menti is taking wrong input, means we are
Not
giving
allowing to put decimal.
not allowing to put decimals.
Okay. Really sorry. No problem. No problem. So this is going to be 2.4, right? It's going to be 2.4. Because if you multiply 0.12 with 20, it is 2.4. Okay, can you put the variance? Don't worry about the decimal. Right. So the answer is going to be 20 into 0.12, which is the P, and Q is basically 1 minus P, which is 0.88. So 20 into 0.12 into 0.88, which is 2.12. 2.112. So mean is equals to N into P, which is 20 into 0.12, 2.4, and variance equals to N into P into Q, which is 20 into 0.12 into 1 minus 2.12. This will come somewhere around 2.112, right? 2.112. Okay. So I hope you understand what is a binomial distribution now. In this class, you don't have to mug up any formula. Just understand one thing, that the binomial distribution is something which is performed on two possible outcomes, right? Or which has a possible outcome that is 2, right? And it is going to be same in every trial, okay? And the trial is independent of the outcome. So this is the one thing which they will ask you, what is a binomial distribution, and you should be able to answer these 3 points. Okay. Now this is a binomial distribution. The formula of it is not required. If they give you 1 or 2 questions to solve, if it is a face-to-face interview, they might ask you a small question, right? Like a flip of a coin or die, right? They might ask you what is the mean and variance of a binomial distribution. Okay. They might ask you what is the function which you use and which package which you use. So generally you should say that we will use SciPy, and the function which you use is binom. Okay. When we give you the statistics interview question, we'll make sure that these are all part of your interview questions. And yeah, so they might ask you simple probability questions. Okay, not too tough, but simple probability questions like what is the probability of getting a sum of numbers greater than, say, 5 if you roll 2 dice. Okay, so I've tried to give you as much as possible what is permutation, what is combination. We should always remember that permutation is something where the order is important, but combination is something where the order is not important. And try to remember it by examples like log, right? Log is something which will be helpful for you to understand permutation and combination. Okay, I will share this PPT with you. And there is some appendix section as well where we'll look where there is example of probability. What is the probability of an event? Why is probability essential? And there are few examples as well, right? Okay. So any question from today's session?
No.
All right. Okay, we'll go through the homework which I have shared with you. Okay, so what is the answer of the first one? Which of the below distribution have the highest interquartile range?
How?
Option
C.
C, right? So 3 is the answer. I hope you understand that interquartile range is the difference between the Q1 and Q3. Okay, so since this has the maximum length, we are considering this as the highest interquartile range. Okay. Your company is gearing up to organize its annual conference this year. They came to you and asked for an estimate of the approximate number of attendees for this year's conference so that they can prepare better with the logistics. They gave you the below data. Which number will you quote them as the possible number of attendees for this year's conference? Answer?
Maybe 700.
Okay. Why?
I thought like because there are no outliers in the data, so mean is a good representative. So mean was nearly 696. So then I
Okay.
thought 700.
Okay. Anyone else? You can post your answer on chat. Not a problem. 900. Okay.
So I tried to do this using two approaches. I tried to find standard deviation. So standard deviation was around 250 or more than that. So I thought 900 can be it. And I also plotted line plot. So as per the, if we are going as per the pattern, then also it is comes around 900.
Right, right, right. Anyone else? So this was one of the questions which was asked to me personally when I was getting interviewed back in 2016. So this was for a company LinkedIn, which I was interviewed with, and they asked me this question. Right? So I was not able to answer the question, but rather I gave an answer which was incorrect. But the interviewer gave me the answer that it is 900. Right? Why 900? As mentioned by, if I can spell your name correctly, is it Aish? How do you pronounce your name?
It's Itesham.
Aitesham. Okay.
Yeah.
Aitesham. As mentioned by Aitesham, that the answer is going to be 900, right? As because we have to take the standard deviation into consideration, and based on the pattern as well, the answer is 900. And also one thing which he personally mentioned is whenever
No, I think Bhargav explained it. I think Bhargav or someone.
Okay, Bhargav explained it. Okay, thank you, Bhargav. So the last point which he mentioned was that whenever we take logistics into consideration, okay, we have to make sure that we are taking exhaustive exhaustive numbers into picture. So this is one of the concept of statistics, where we try to make sure that whenever we are creating something related to supply chain and statistics, we always take the higher numbers. Okay, the answer is 900 from a standard deviation point of view also, but from a more general logistic domain perspective, the answer is going to be 900 only. Okay, we cannot go by the mean, because at times we might see that people more than 900 might attend, but since we take 900 into consideration, we took a very exhaustive number uh, just to make sure that we are able to cover the entire sample space. Okay, a little tricky one,
Sir,
but yeah.
so that means like to solve these types of questions, we just don't rely on mathematics. We have to
Exactly.
apply our brain, and circumstances should be taken into consideration too.
Right. So I tell you that data science is actually a mix of three things. One is programming, the other is statistics, and third is domain. Your entire scenario will change when the domain changes. So the way a statistician thinks for a insurance product is very much different from what it thinks from, say, for a banking product. Okay, so these are the things which you need to understand whenever we try to answer statistical questions. So that's why you will see that more and more experienced people are required, because they have a lot of intuition in data science and machine learning.
So what answer did you give on in your interview? Like what
I
was
gave
your answer?
I gave 700. Okay, because
Uh,
I got panicked in the interview and I just used the mean formula there, and it was 700, and he asked me to think about it, and then I said, no, this is not the right answer, but let me think. And somehow, since he gave me an option at the end that these are the four options which you have, I took the courage to say 900, but I was not able to explain why it was 900. Okay, so this is one learning
oh,
which I had, so thought of giving you
okay.
this. Okay, next is, you are trying to estimate on an average how many movies does a data scientist watch in a year. Since you do not know how many data scientists are there in the entire world and the movies watched data of all these people, you decide to make do with inquiring your fellow batchmates. You ask 10 of your batchmates the number of movies they watched in a year, and below is the result. Can someone tell me what is the sample variance?
15.
15, right? Which formula did you use?
Variance formula.
Okay, sample variance. What is the sample variance formula? Can someone tell me?
Difference of difference between all points and the mean, that is squared divided by n.
Is it n or
N
n
minus
minus
1.
1?
And sorry,
N
n
N
minus
minus
1. So what is the answer with n minus 1?
I think I got 17 by n minus 1.
N minus 1, you will get 17. Okay, so the answer is 17. Hope you all understand this. So what you need to do, you need to first find out the mean. Not sure. Okay, first you need to find out the mean. Okay, say for example, the mean here is, say, 10. Okay, then you will deduct 10 to each of these values, right? 12 minus 10, 17 minus 10, 18, 8 minus 10, and so on. Square them up. Okay, sum them up, divide by the sample variance. So you have 10 data scientists here, right? So you will divide this by 9, and you will get the answer is 17 here. The answer is going to be 17. Okay, next is, from the below graph, what is the approximate average height of people who weight below 40 kgs?
D, 2.4.
Why?
So there are like 5 points from the bottom, taking average of them is almost
Right.
around that.
Right. So the answer will come as around 2.4. Okay. So actually the grade didn't work here. Actually, I could have given the grade here. But since you got the logic, right, you have to take the sample which is below 40 kgs here, add them up, and find the mean. Okay, this was very easy question. I will share this assessment solution. So out of other than these 4 questions, you have 6 more questions. Okay, I will share this with you. These are some of the questions are actually interview questions which were asked to my students and myself. So I've created this. There are few questions which you will be able to answer when we go through, kurtosis, and you will be able to solve at least eight questions right now. Go through them. If you have any question, do let me know. But these are real interview questions. Okay. So these type of samples we'll be sharing with you for each of the individual topics. A lot of the questions are actually asked from inferential statistics. So next day we will look into a Poisson distribution. That is tomorrow. We will look into how to create a standard normal distribution or a normal distribution. I've already gone through it in the earlier class, and then we'll directly jump into hypothesis testing. Hypothesis testing is going to be a with 1 sample and 2 sample. It will probably take 3 weeks of time for us to go through the entire session of hypothesis testing, and we'll complete statistics within 24 to 25 hours of total lecture. Okay. So do you have any questions from today? Are we good?
Yes,
I tried to go a little slow, taking time. Okay. All these slides I will be sharing with you. Make sure you have these slides handy. For the type of interview questions which are being asked, I'll prepare 50 questions for you, which are already with me. I will just make sure that these are all updated with the latest one which I'm getting from my students. And once that is done, I will share the statistics question with you, and you will be able to answer these questions on your own. You'll have the answers as well. If you find any discrepancy in the answers, do let me know. Sachin, I will get back to you with the proper explanation of the previous one. But as I said, this is a random sample. We are drawing 2 at a time. I will also check my answer to make sure that I'm not incorrect. Okay.
Yes.
Okay. Thank you, guys. We will see you tomorrow. I will share the Python notebook with you and the slides as well. Thank you very much. We'll see you tomorrow, sharp at 9.